Hello, and welcome to our webinar, Problems with Kurtosis as a Random Vibration Specification. My name is Mark Pike, and I'm the Marketing Manager at Thermotron, and our presenter today is Dr. Ben Schenk, a Vibration Engineer at Thermotron and an expert in physics. He earned his PhD from Stanford University. We are very excited to have you, and we hope that you enjoyed today's webinar. We will be taking questions throughout the webinar, and Ben will be answering them as time allows. Alright, well let's get started. Ben, I'm going to hand it off to you. Thanks.
Thanks, Mark. I want to give a brief overview of what I'm going to cover today. I realize the entire audience may not be familiar with theories of vibration damage, or may not even be aware of what non-Gaussian or kurtotic testing is. So I want to review those briefly. I'm going to make some very broad claims about damage equivalence, and so I want to stop and take a moment to discuss what that means. Then I want to jump into how you might replace a kurtotic test, giving a very simple example about ways you can run tests on your shaker faster than using kurtosis. And then finally, I want to get into a number of issues that we've found as we developed our kurtosis algorithm, using it in specifications and problems with running it specifically on an electrodynamic shaker. So maybe it's just the physics professor in me, but I'd like to start by just explaining how a shaker breaks things, because I think there's a lot of confusion on this topic. A shaker is not the same as a coupon test, where you break a material by grabbing both ends and pulling it until it breaks. A shaker typically only excites the base of a product, or some limited anchor points. Parts of a product that break usually fail because a stress is induced because they have a mass attached to them, and they are insufficiently strong to accelerate that mass along with the rest of the product. So products sustain vibration damage not when they are simply pulled too far, but when key resonances within the product are excited to high modal velocities. Now I've quoted a paper there, Howie Gaberson and Chalmers, which is a fairly old paper at this point, citing modal velocity as a criterion of damage, and the equation is up there in the top right. It turns out none of the conclusions of this talk change if you define stress in terms of peak acceleration or in terms of maximum displacement. But because I think there's a good argument for using modal velocity as a criteria of stress, I'm going to use the words modal velocity, pseudo-velocity, and stress interchangeably throughout this talk. So next, given a measure of stress on a shaker, I want to talk a little bit about how fatigue damage is accumulated within a product. For a number of materials, stress number curves have been measured given some fraction of the ultimate stress of the material, how many times you have to stress the product in order to cause failure. And these break down roughly into 3 regions. Well, technically 4 regions. Obviously, the highest region is if you apply stress in excess of the ultimate stress of the product breaks. And you might do that with a shock test, but that's not really what we're talking about. As you come down in stress level, you reach a region, and go ahead and look at the plot on the right-hand side of the screen, that low cycle fatigue region. So at fairly high stresses, but not the ultimate stress of the material, products are damaged by macroscopic plastic deformation. And so when you see a test that is a series of high-level shock pulses, that's what you're testing against. As you come down in stress a little bit more, you enter this high cycle fatigue region, where the product isn't macroscopically deforming as the test progresses, but rather microscopic cracks are propagating through the material until they reach some critical length, at which point the next stress cycle causes an uncontrolled energy release and the product fails. Now, this has been measured for a number of materials. Note that that high cycle fatigue region usually has a cycle life which is proportional to 1 over the stress induced raised to some power. Sometimes you see this as m, I'm going to use b, but this is the fatigue exponent. And so you see on the graph, mild steel has a fatigue exponent typically around 12, aluminum alloys typically about 10, other materials maybe 6 or even as low as 4. While 4 to 12 is a fairly typical range, products that are damaged by random vibration tend to be in the lower end, and so you tend to see 4, 6, and 8 used as assumptions in the literature. A couple things I want to point out about this curve. First, it doesn't go all the way down to 0. The high cycle fatigue region typically only covers a factor of about 3 in stress, which is the same as modal velocity. Below that, if your product happens to be steel, you hit an endurance limit and there is no number of cycles that will damage the product. But even if you have a product that isn't steel, you enter a high endurance region where, yes, you still are accumulating damage, but so incredibly slowly that it kind of ceases to matter, and certainly the approximation that you made in the high cycle fatigue region is no longer valid. Also, within this region, a twofold reduction in stress will often give a 100 or 1,000-fold life increase, and so even if you have stress cycles throughout that region, it tends to be the higher stresses that dominate the damage calculation. Okay, well that's all fine if you are applying the same stress over and over again, but the subject of this talk today is random vibration. So what do you do when you have stress cycles of all different magnitudes that you're applying to the product sort of intermixed with each other? The key that's usually used is Miner's rule. Stress cycles are treated as being independent and their damage is treated as being cumulative. So for example, if you have a stress cycle, let's say you have a sample of aluminum, just to pick a number off the graph, and you have a few stress cycles at 0.4, so 40% of the ultimate stress. Each one of those cycles is going to do about 100,000th of a life of damage. Whereas any stress cycles that have 50% of the ultimate stress are going to do about a 10,000th of a lifetime of damage. Now in practice, you don't normally know that normalizing constant S naught, so ideally you'd like damage to add up to 1, and that means the product fails. In practice, you have some arbitrary constant that damage gets up to, and then a statistical distribution of when the product fails. But nevertheless, you can think about damage in terms of adding up, that equation at the bottom, the number of stress cycles at each given stress times the stress raised to the fatigue exponent B. So how does this work out? I've provided here an acceleration trace which is intentionally not from a shaker. This is from an RS table, so repetitive shock. And if you don't know the resonant frequency of your product, but you nevertheless want to calculate stress cycles, you could just pick a number of resonant frequencies. I've picked here 100 Hertz and 150 Hertz. You would just create some list all the way through the frequencies that you're interested in, and use published filter algorithms to calculate what their velocity relative to the base would be as a result of the particular acceleration trace you're looking at. Those cycles can then simply be added up. There are a number of algorithms. I'm using rain flow counting throughout this talk, but there are others. Once counted, the cycles are treated as being independent according to Miner's rule, and so you get, based on these traces, you turn those into histograms, shown at the bottom there. Now I'm showing the histogram for 1,000 Hertz, and I'll explain why in a little bit. You then create a fatigue damage spectrum where each of those histograms is added up using the Miner's rule equation, and then plotted as a function of frequency. Now, you often see these histograms in literature without what I consider to be very important guides for the eye. So let me show you how to read these. Remember that we're really only interested in stress cycles that fall along that high cycle fatigue region. So in the picture at the bottom right, if those stress cycles at 120 inches per second don't instantly destroy the product, then any stress cycles below about 40 can be completely ignored because they fall below the endurance limit. And in practice, unless you're using a fatigue exponent of 4 or 5, you can usually almost ignore stress cycles down near that cutoff point because they end up just not contributing much to the calculation. So as you see these histograms throughout this talk, remember you're looking at the right-hand side of most of those graphs. Okay, and then here's an example of how that addition might be made. I've added Miner's rule, the equation, to the graph, and then on the top you would plot. So this histogram is one point on that plot. You would then take all of your other histograms and make a continuous line. Note that the result depends fairly heavily on what fatigue exponent you use, but this is a good way, for example, to learn that this table is much better at damaging products that resonate at 1 kilohertz, so 1,000 hertz, as opposed to products that resonate at, say, 3 kilohertz, because the fatigue damage spectrum is much higher at 1 kilohertz. Okay, so now I want to take a moment to talk about non-Gaussian testing. Well, that's not quite true. Actually, I want to talk about kurtosis testing specifically, which is a subset of non-Gaussian testing. The idea here is that given a fixed PSD, you can increase the damage done by that test by increasing the incidence of extreme peaks. Now, this is normally measured, at least, in controllers on the market today by the statistical fourth moment kurtosis. You can think of kurtosis as a way of measuring power in two different ways in such a way that extreme peaks get more heavily weighted. So I've got the formula on the screen there. Kurtosis K is the average of the fourth power of acceleration divided by the average of the second power of acceleration squared. So this is the fourth moment normalized by GRMS to the fourth. This gives you a unitless metric which is independent of the power level of the test and basically tells you how effective you have been at getting extreme peaks into your test. As an example, on the bottom left, I have a Kurtosis 9 test, 1 GRMS. The same PSD, still 1 GRMS, Kurtosis 3 in the center. Kurtosis 3 is the value for a Gaussian test, and that's what you're running on a shaker if you're not, quote, running kurtosis. And you can see in the normalized histogram, which is called a probability density function, which is the bottom right graph, that Kurtosis 9 test contains 6, 7, even 8 G peaks that just don't appear in the Gaussian test. And so, yes, that K equals 9 test is going to do more damage for the same PSD than the Kurtosis 3 test. Now, I need to be a little careful. Remember that just having a high acceleration doesn't cause damage. It's getting the product into resonance at a high velocity. And so we need to be careful when we're creating these rapid extreme peaks that they don't happen too fast. And so I want to demonstrate that using a little thought experiment. So in the center column here, I have a product that resonates at 100 Hertz and is, you might call, moderately damped, quality factor of 5. In the right-hand column is another product that also resonates at 100 Hertz, but is more lightly damped, has a quality factor of 15. And then in the left-hand column, I have two tests that I would like to apply to these products. This is sort of a toy kurtosis model in that I'm going to go from a low level, in this case off, to a high level, in this case a 10G sine wave, and then back to a low level, which is off. So this is sort of the simplest imaginable toy kurtosis model. In the first test, we are going to leave the sine burst on for 20 cycles at resonance. And you can see in the middle column, the quality 5 product gets up to a response in about 5 cycles, and then when the excitation goes away, it takes about 5 cycles to get back to the lower level. The quality 15 product gets to a higher total response, but it takes about 15 cycles to get there. And then when the excitation goes away, it takes about 15 cycles to fully ring down to the lower level. So if you think that you're going to get enhanced damage out of your test by performing the test in the bottom left, where you turn the shaker on for 3 cycles and then turn it off again, you can see that your quality 5 product, bottom center, gets most of the way up to its full response and then rings down. Your quality 15 product, it gets higher than the quality 5 product, but it doesn't get anywhere near the response that you thought you were getting when you said, I'm going to apply a 10G sine burst. So when you're running kurtosis, it's important that any change you make lasts longer than the quality factor of the product you're trying to break times the period of resonance. So with a little math, that top line there, you can see that whatever change you make needs to be slower than 1 over the resonance frequency, the resonance width of the product that you're trying to break. Now, if you've run a vibration controller at all, you've probably heard someone say that you need to specify enough control lines so that at least one control line falls near the center of each resonance of your product. And so you can say delta F of the resonance has to be greater than delta F of your control lines. Now, in most kurtosis controllers, there's going to be a setting called kurtosis frequency. You might see it called transition frequency. They're similar in effect, but they are defined as the inverse of the fastest rate of change where the controller goes from a low level to a high level back to a low level. And so the good rule of thumb there, given the above, is that you should specify a kurtosis frequency that is comparable to the control line width of your test. Now, in most controllers, you have to set that by hand. If you happen to be using the inverse windowing method, which is what Thermotron uses, that actually happens automatically. I'm about to make some very broad claims about damage equivalence, And so I'd like to take a moment to stop and talk about exactly what I mean. In much of the literature on fatigue damage spectrum, two tests are considered to be damage equivalent if the fatigue damage spectrum trace, so that sum over all the histograms, is the same for the two tests. Now that assumes that you know what the fatigue exponent is for your product, and in many cases that isn't known or isn't even knowable because the product is made of multiple materials. And so for the next few slides, I'd like to say that two tests are damage equivalent only if all properly controlled histograms, so provided that you actually have a resonance that is fully seeing the kurtosis that you're applying, if all properly controlled histograms are identical. And this could get very esoteric here in a few minutes, so I want to give a specific example that will be the baseline for this comparison. So I have here the Chinese JJG 676 test, which is typically a test of shaker dynamic range. I've picked it because it has a weird shaped PSD. Because I want to show you that the remarks I'm about to make do not only apply in flat PSD circumstances or with other limitations. We're going to have a standard test that is 10 minutes long, runs with 800 control lines on the 2500 hertz range, so it'll have a bin width of just over 3 hertz, and I'm going to specifically look at 3 products. One has a resonance at 325 hertz, quality 10, so it takes in most of that long drop down into the JJG well. Another takes the other side of that well, but includes the kink, and that'll be about a 60 hertz wide resonator. And then just to show that this isn't particularly quality dependent, I've got a very sharp resonator, quality 100, out at 1200 hertz. That will only have a width of 12 hertz, but because my test has a 3 hertz bandwidth, or bin width, sorry, that is still considered a properly controlled kurtosis. Note also that this profile I have scaled to 1 GRMS, so from now on, any slide that reads acceleration can also be read number of sigmas. So let's just start with one that we know. Increasing the kurtosis of a test without increasing the PSD increases the amount of damage that the test does. And so here we have in the top left a kurtosis 9 trace and the kurtosis 3 trace from before. These are both 1 GRMS. We have the acceleration histogram in the top right that we saw before. And then down in the bottom row, I have the response histograms for those 3 resonators on the previous slide. And you can see that the kurtosis 9 trace has damage cycles that are nearly twice the value of the kurtosis 3 trace. And so if someone tells you, yeah, the kurtosis 3 or the Gaussian trace really doesn't damage my product at all, but when I turn the kurtosis up without changing the PSD, I suddenly am able to damage the product. Yes, we should believe that because the kurtosis 9 trace has damage cycles that are just not available in the Gaussian case. But, when you look at that kurtosis 9 trace close up, it's got a lot of downtime in it. Yes, there's some big peaks, but it actually spends most of its time not doing a whole lot. And so, one thing you might try is, can I collect all of that downtime together and get rid of it? So, what I did for the next slide is took the acceleration histogram for the k equals 9 trace, so the black trace, top right corner there, and just fit lots of Gaussians of different widths to it. Now for you math types out there, I know that a multi-Gaussian fit is not an orthogonal basis, and there are other ways to do this, but just for the sake of example, I'm going to pick Gaussian levels that are 0.25 GRMS apart, so a quarter of the test level, and just see if I could reproduce that histogram. And there's the result. So actually, it turned out 25% was a little bit too close together. The fitting tool told me I didn't need all of those levels. But you can see on the top, the kurtosis test that you're replacing, and on the bottom in blue, a quote Gaussian test. The whole test duration has kurtosis 9, but at any given instant, you're just running a Gaussian test with various power levels. And you can see that you start at the 225% level, and you end up working your way all the way down till you're really not doing a whole lot of damage. Now, before we go any further, obviously, PDF is not the correct metric of damage, so let me for the damage equivalence that I promised. Top row, there's the k equals 9 test, there's the Gaussian level test in the middle, and then on the right is the PDFs. You shouldn't be surprised that the PDFs line up because the point of that fit was to make them line up. But in the bottom row, you see the 3 resonators that we were looking at. The black trace is the Kurtosis 9 test, and the blue trace is that level schedule. And except for some small number statistics at the very bottom, those line up perfectly. And so for any conceivable fatigue exponent, that level schedule is damage equivalent to the kurtotic test. But let's go back and look at that level schedule. So we'll go back a slide here. You could run them in any order, but I've listed them from highest to lowest and shown them on the graph that way because if that 225% level doesn't destroy your product instantly by going over its ultimate stress, we can argue about the 75% level, but you really have no business running the 50% level. You are literally doing no damage at all. And so if you're a test engineer and you wouldn't order that level schedule run to completion, even including that bit at the end where the shaker isn't really running, you really have no business ordering a Kurtosis 9 test. There is a faster way to do it. If nothing else, you could make a level schedule out of it and just run the levels that are relevant. So maybe, in this case, 225, 150, and 125. Maybe 75. But you could save 50% of your test time just using this very crude technique. And given the kurtosis algorithms that are on the market, you can make this schedule for any kurtotic test. So it turns out using kurtosis is never, in any situation, the fast way to damage your product. I realize that I tend to stay away from having to know what the fatigue exponent is, but many of you out in the audience are perfectly happy using fatigue damage approximations to assess damage to your product. If you're willing to do that, you can save even more time. So let's take that same level schedule. If you happen to know, or you're willing to assume, a fatigue exponent of 4, then you don't have to run that 150% level. You could instead run the entire test at the 225% level and just adjust the time that you would have run the lower levels, reducing them because you're running at a higher level. And so in that right-hand column, I have made the adjustment using the correct or the assumed fatigue exponent. And you find for this particular test, if you're willing to run at the 225% level and you know a fatigue exponent of 4, you can reduce the duration of that test to 11.7% of its original time. So your 100-minute test suddenly becomes a long coffee break. Now, I made a claim earlier that you could generate these level schedules for any kurtosis. Here are the level schedules for a variety of kurtoses. Now, I need to be very careful here. Thermotron just released a kurtosis algorithm, and this is not the only solution, but an exact solution if you have Thermotron's kurtosis algorithm. Now, it's a paid extra, and to my knowledge, no one has paid for it yet, so the number of people that this chart is useful to exactly is 0. But we did spend some effort making sure that our kurtosis looked very much like other controllers. And so this gives you at least a flavor of how much time you could save by replacing kurtosis. And actually, the fact that this isn't usable on other people's controllers is a big problem, which we're going to get to in a little bit. If you are willing to embrace the fatigue damage spectrum, you obviously can save more time. Note that for kurtoses that you typically see in specs, kind of in the 7 to 9 range, typically for fatigue exponents between 4 and 8, which is what you typically assume, you're saving about 90% of your test time. You're running for 10% of that time. Now, you do have to turn up past the 200% level, and someone out there is thinking, okay, but my shaker can't actually do that. So let's talk about that for a minute. Speaking as a representative for a company that makes shakers and, as an aside, makes controllers to control them, I want to talk for a moment about the process of running kurtosis specifically on an electrodynamic shaker powered by amplifiers. which is a stack of inverters. The peak current limits of most electronics are dominated by the inability to get heat out of very small components. In the case of an inverter stack, the small component that you're usually worried about is switching transistors, because at this point, I think everyone's using Class D switching amplifiers to power shakers. I'm going to use the numbers for Thermotron because I know them, but these will be very typical of the industry. Thermotron's inverter, standard inverter, has an 85 amp RMS rating. The switching transistors inside it are rated to withstand repeatedly 400 amp peaks for 1 millisecond. And it's fairly easy, given a kurtosis algorithm, to say, what is the crest factor? So given an RMS rating, what multiple of that RMS rating am I going to see on a routine basis? And I've somewhat randomly selected the once per minute excursion. You sometimes see once per hour excursions depending on what someone's trying to optimize. You can see that with our 400 amp transistors, even running a Gaussian test, kurtosis of 3 flat out, we are getting near the current peaks of our transistors, and you run the real risk of causing damage. So if you run kurtosis higher than that, and you're trying to run flat out, you are going to damage the amplifier. Now, they make transistors that go as high as 600 that are available to us. To some degree, that maximum kurtosis of 6.3 is fictitious, because if we updated the inverters to use those 600 amp transistors, we would probably be able to increase the RMS rating as well, and so you'd be back down where you started, just at a higher RMS level. The upshot of this is you can't run kurtosis at the full GRMS of the system, and it has to be derated. Now, some amplifiers have a spec not for peak current, but for instantaneous RMS overhead. Typically, this is set at about 50% over, so a value of 1.5. And that rating means if you run at this level for more than 1 or 200 milliseconds, you're probably going to damage the inverter. So I'm showing here on this graph, given, again, Thermotron's kurtosis algorithm, but other algorithms will be similar, what the highest and lowest RMS extremes you're likely to see are. And you can see that you don't really have to turn kurtosis up very far, to a value of 4, and you're already above the instantaneous RMS overhead of most shakers, of most amplifiers. Again, the upshot is the same. You can't run at full GRMS, and so as soon as you turn kurtosis on, the system has to be derated. Now, this actually caused a problem for me, because when I was developing the kurtosis algorithm and wanting to do testing at full level, modern amplifiers have a current donut built into them, and if you exceed the instantaneous RMS overhead, they just abort the test. And so when I was running with one of our newest generation of amplifiers, I couldn't actually run kurtosis near full level, and in fact, backed the GRMS all the way off to the point that I wasn't accelerating the test, and I kept getting these instantaneous RMS overhead trips. So I report this to the R&D group and say, hey, does anybody have an older inverter that doesn't have this safety feature so that I can continue testing? And you know what? It was amazing. Suddenly, all of the old inverters in the building were needed for something else. No one wanted to, given that report, wanted to let me have one of their inverters. So I don't have a picture of a burned up transistor to show you. I will allow you to judge for yourself how much sympathy you're going to get if you call in with a warranty replacement and we find out that you were running kurtosis at the time that your amplifier failed. So hopefully, if you're a lab manager, I've convinced you that you really shouldn't be using kurtosis unless it appears in a specification. Let me talk for a moment to those of you who write specifications, because I'm starting to see kurtosis turn up in specs that our customers need to run. So consider the two traces, the top left and the middle there. The blue trace is taken from the control algorithm that Thermotron just released, Kurtosis 9.1. The black trace is also Kurtosis 9.1, same PSD, fulfills all the same specs. Its crest factor is 36% higher than if you were running on a Thermotron controller. Now that could very well be field data if you somehow generated a spec from the field. Frankly, that could be somebody else's controller, because we've tried to a limited degree to match our damage to what we see in papers written by other manufacturers, but that's an inexact science at best. And so, if you're using kurtosis in a specification, be aware that tests run on different controllers are going to do different amounts of damage to the product. And now you might think, well, if the blue trace is a typical controller and some of my vendors are using the black trace, well, they're over-testing, but I don't care. The problem is, if you have the technical know-how to build a kurtosis controller at all, you also have the ability to build this black trace. Now this is 9.2, it's not quite the same, and I'll explain why in a moment. It turns out it's pretty easy to write a kurtosis controller that doesn't do nearly the damage that anybody thinks of when they say, quote, I want a kurtosis of 9. And you can see on the PDF and down in the bottom row, that black trace just isn't even achieving the same level of damage. Its peak response isn't even the same. It will do substantially less damage than what I'm calling a typical controller. Now I want to be very careful. I'm wearing my white hat right now. The reason I don't have a nice clean PDF for these and they're not pitched to exactly 9.0 kurtosis is I've been very careful not to develop these algorithms, but they are algorithms that we considered at the beginning of our kurtosis project, and basically anyone who can create a kurtosis controller at all could easily create a low damage version of kurtosis, and you wouldn't really be able to tell. Even if people aren't acting maliciously, just the fact that different manufacturers don't share information with each other means that all of their kurtosis algorithms will do different amounts of damage, and so it's not really a valid test specification because it doesn't specify an amount of fatigue damage. All right, we're getting near the end. Before I wrap up, I want to talk about the process of adding kurtosis back into a test. So let's suppose that you took my advice from a few slides ago, and you had a kurtosis 9 test, and you want to replace it with a Gaussian test that runs at a higher level, in this case the 240% level. And for the sake of having an example, we'll assume b equals 8, so you are running 4.4% of your test duration. So you have turned an overnight test into an overlunch test. And someone says, but I could further accelerate your test by adding the kurtosis back in. I want to examine that claim for a moment. Here in black is the kurtosis 9 test that you replaced, and in blue is the Gaussian test that you replaced it with. And I've gone ahead and scaled the acceleration histogram, or the PDF on the top right there, to account for the reduced duration of the kurtosis 3 test. Now look at the bottom row. You see that the blue traces have many, many fewer cycles at low pseudo-velocities, which you expect because they're shorter and don't have a lot of downtime in them. But the endpoints on the bottom right of each graph are essentially the same. And if I could show you a longer trace of data, those would line up even more. If you want to increase the kurtosis of that blue trace, if you don't change the total GRMS level, then you are going to extend that bottom right intercept out beyond the test that you were replacing, and that will legitimately be an overtest. Yes, you'll test faster, but that's a real overtest. If you don't want to move that bottom right intercept, but you want to increase the kurtosis, what you end up doing is just shoving more and more of the damage cycles down to lower pseudo-velocity, and so you're going to have to run longer to achieve the same damage. The process of fatigue damage replication already sets the GRMS level as high as possible without effectively overtesting, without exceeding those highest stress levels. And it's fairly easy to show, and this is one proof by example, but it's easy to show analytically that any attempt to increase kurtosis without changing GRMS causes an overtest, and any attempt to increase the kurtosis without causing an overtest results in a reduced test level and a longer test duration. So in a fairly one-to-one way, the degree to which you are willing to add kurtosis back in is the degree to which test duration doesn't matter to you. Now there may be reasons for that, but if your goal is to test quickly, this is never a good idea. So in summary, increasing kurtosis is a quick but non-unique way to model variable vibration power. If you are running on an ED shaker, you can, I think it's safe to say, always replace high kurtosis testing with a more efficient Gaussian test that does the same fatigue damage in less time. And using kurtosis as a specification is not a reliable way to get the damage that you want to validate your product against. Well, that is the end of my prepared remarks. I'm going to turn this back over to Mark for a little bit.
Well, thanks, Ben. We're going to let Ben catch his breath here for a little bit, but we appreciate the information. A lot of great information out there. As I mentioned before, if you have any questions, feel free to submit them now. And although we may not get through all the questions, we will be providing a Q&A document afterwards to all the participants of the webinar. We'll also be posting this information on kurtosis on this topic over at thermotron.com/kurtosis, as you can see in the bottom link. Also, if you have any questions or want to learn more about Thermotron, please contact us at info@thermotron.com or just visit our website. Ben, are you ready for the first question?
Sure, Mark.
All right. Well, first one that came in is, why did you add a feature to your controller that you think no one would use?
Ouch. Well, actually, this story is a little bit embarrassing to me. I left academia to join Thermotron about 18 months ago, and my very first assignment was find out what kurtosis is and develop an algorithm to control it. This presentation is actually an expansion of a memo I wrote to my boss a month or two later, and I explained how a kurtosis feature might be constructed and, frankly, why Thermotron shouldn't develop one. And as far as I'm concerned, end of problem, next assignment. A couple months later, that memo got circulated to some of the senior Shaker engineers, and one of them pulled me aside and explained about the wonderful world of specifications. Apparently, you can't modify an OEM test just because you think the spec is ill-defined, which makes sense, but yeah, I made all the arguments about, this is a bad idea, we shouldn't be doing this, and he just kept saying, well, tell that to the people who write specifications. And here we are, and hopefully I just did. At any rate, the short answer is, we are trying to get the word out that kurtosis is a dangerous and ineffective specification, but while it's still in use, we want you to be able to sell your product. Just be careful and make it very clear to the application engineer how you intend to use kurtosis, and we can help you through. I did spend some time looking at PDF graphs from existing controllers, so our method is at least vaguely like what the spec writer might have had in mind, but not surprisingly, the people who make those other controllers, they don't really want to share specific control parameters with us. So we did the best we could, but no promises. And frankly, the controllers that are out there already have pretty significant damage variation, so just sort of aim for the middle of the pack, and if you need it, use it, and if you don't, great.
All right. Well, hopefully this next question is not going to be as embarrassing. But what is the inverse windowing, and how is it different from other kurtosis methods?
Yeah, that's a great question. I think I have a slide about that. Yes, there it is. Okay, so when a controller generates continuous vibrations, and this is not just a kurtosis controller, but any random controller, it has to build discrete buffers and then somehow stitch them together. In order to avoid sudden jumps, buffers get multiplied by some window function. I'm using the Blackman window here, but there are lots of options. As long as the window function goes to 0 at the edges, then you can overlap buffers in such a way that the average power at least stays constant. So on the left side there, I'm showing an example of how individual buffers get stitched together normally. Note that the length of each buffer is always always the inverse of the frequency resolution that you set, because you have to use an inverse Fourier transform to create them. So if you want to make sure that you're turning the power up and down slowly enough, the buffer length is sort of a natural timescale. So to make kurtosis, we just multiply each buffer by a random positive number. And actually anyone can do this. Two rules. First, whatever distribution of multipliers you use has to have an RMS value of 1 so that you don't change the total test level. Second, you have to have at least one tunable parameter so that you have some empirical handle to control kurtosis. This method has been in the public domain for years, so anyone who wants to make just a quick and dirty kurtosis controller can use it. I think most of the controllers on the market right now create a Gaussian random independently, and then they amplitude modulate it with some separate function, and then make sure that that never varies faster than a user-defined kurtosis frequency. That seems like an invitation to get the user in trouble to me, and that's why we went with inverse windowing.
All right. Thanks, Ben. Next question. You said kurtosis derates the shaker, but doesn't it really just derate the amplifier? Couldn't someone add additional amplifiers to make a shaker that didn't have to be derated when it ran kurtosis?
No, actually, that's a really good question. In theory, yes, there are arbitrary shakers where you could do that. In practice, well-designed shakers tend to run out of current and voltage at about the same time. Now, obviously, that's a very general statement. Under typical loads, well-designed shakers typically run out of current and voltage at about the same time. We actually studied the problem of building a shaker specially to run Kurtosis. So the test bed for our study was a DSX 4000, which, as the name implies, can run flat random at a 4,000 force pound RMS rating. So DSX 4000 uses one inverter. It's a Thermotron inverter, so 85 amp RMS. It needs a 5 horse blower to keep it cool. If we stack a second inverter on it, you might think that we could run for short periods at 8,000 force pounds, but very quickly we'd hit the rail voltage and start clipping. You just wouldn't be able to control the test. All right, no problem. We are a shaker manufacturer. We'll just redesign the armature to have lower impedance. Of course, when you do that, you have to reduce the wire length. So now you need a third inverter, because remember that force is proportional to both current and wire length. You reduce the wire length, now you need a third inverter to get that 8,000 force pound burst so that you can run Kurtosis. But you've now engineered your way to the point that if you just upgrade to a 15 horse blower, you have a DSX 8000, which, again, as the name implies, can run 8,000 force pounds RMS flat random. So your quote-unquote special Kurtosis machine is really just a higher powered shaker with an underpowered cooling system. And at this point, you should really just buy the premium shaker and run it flat out for whatever that is, 10% of the time you were planning to run Kurtosis.
Okay, next question. What is a unique way to model variable vibration power?
Oh, right. Yes, I said Kurtosis is a non-unique way to model variable vibration power. Well, there are ways to create stochastic random processes that would recreate all of the fatigue histograms in detail, and even model specific burst events, transients on a random. Off the top of my head, you could use short-time Fourier transforms, some sort of wavelet. You could make a response spectrogram. You'd probably need a ridiculously large sample of data at that point. Probably for most applications, ballparking, you'd probably need about 24 hours of data. But then you could play that back with randomized phases, and you'd get something that looks and sounds like real-time data, but could go on forever without repeating. For many types of data, if you've got some, like a sprung mass, anything where the response is dominated by some fixed mechanical system, you could maybe get away with a regular Kurtosis algorithm, except instead of specifying just the Kurtosis, you explicitly lay out the detailed distribution of window multipliers. Now, if you're into that sort of thing, there's a lot of really fun math there, but I think we're kind of losing focus. We are now talking about a very computationally expensive way to spend a long time to test your product. So this is fun. I love to talk about it, but if your goal is to quickly test against something that has the same harshness as the real world, you should really just turn your normal Gaussian test up as high as it can go without going over the peak stress levels and just let it run.
All right, well, we have time for a few more questions, so here's the next one. Does making level schedules only work for your version of Kurtosis?
No. Provided the kurtosis frequency is set low enough that the resonator is being considered, so the product you're trying to break actually sees the full effect of kurtosis, shuffling the distribution of levels around will always leave the fatigue histograms unchanged. So another way to look at this is that to be effective, a kurtosis controller has to change the power level more slowly than the characteristic function of the thing being shaken. So if you've taken analytical mechanics in college, that's sort of how you'd think about it. So at any given instant, the product is effectively in a Gaussian vibration state with a quasi-static or nearly constant GRMS level. And as long as you get the same distribution of power levels, it doesn't matter from a fatigue standpoint how you got there. You could do it by window multiplication, amplitude modulation, level schedules, although that's a bit crass maybe. Just be aware that you won't get that same distribution of power levels if you switch from one controller to another, or of course if you switch from a real-world measurement to a vibration controller. Actually, you're most likely to get into trouble switching from real data to a controller. And that's one of the things that freaks me out when I see kurtosis suddenly appear in a specification. At least all the controllers have some common vision about what kurtosis means, right? They're smooth PDFs, they roll off gently, the shape of the PSD doesn't change wildly with time. Real world has no such compunctions, so you can't just take a kurtosis from real world data and stick it into a test designed for a shaker and expect to get the same damage, let alone switching from controller to controller and expecting the same damage.
Okay, it looks like we have time for one last question, so here it is. How do you know the blue trace is the right one to produce it? Sorry, kurtosis. What if I want to run kurtosis with more or less damage?
See, this is the problem. There's no way to define a right one. Let me go back to that slide. There it is. All three of those methods, well, the two shown there and the one on the previous slide, they're legitimate window distributions that we thought about using to generate kurtosis. We selected the blue trace, the one that's on both slides, because we think it's about the same as what we see in literature for other controllers in terms of damage. That doesn't mean it's a good match for kurtotic data you gathered in the field. To get to the second part of the question, for now, we've constructed at least our version of kurtosis so that the damage is not tunable, beyond setting the PSD and the kurtosis value. The black trace, not this one, the black trace on the other slide, does have a second parameter that allows, I would say, limited damage tuning. If we decided to make kurtosis with widely tunable damage, we would probably design it to switch randomly between the various methods. I suppose if you wanted to purchase every controller that has kurtosis in it, you could just measure which one does the most damage and then which one does the least. That would amount to damage tuning, sort of, but the only reason I can think of to do that would be to get around a test spec, so I really wouldn't encourage it. I think I'm just going to leave this on, unless you are required by specification to use kurtosis, you are always better off setting a Gaussian level that does the damage you want.
Alright, well Ben, that sounds like a great place to end this webinar. So thank you so much for your help in providing all this information to all the listeners. And we will have some more information on this whole topic at thermotron.com/kurtosis. And also, if you have any questions, feel free to email us at info@thermotron.com. And for more information about Thermotron, visit our website. And we hope you enjoyed the presentation. And thank you so much. Have a great day.